The rudder gives directional control about the normal axis. The rudder is not used to steer the aircraft like a boat. The main use of the rudder is to balance the aircraft, to maintain coordinated flight, but in addition, the rudder is used to fulfill several other particular functions. The first use of the rudder we will look at, and perhaps the most important, is to give the pilot the ability to maintain directional control in the event of an engine failure on a multi-engined aeroplane. A propeller-driven aeroplane is illustrated, but the same would be true if it was powered by gas turbines. The left engine fails and a left yawing moment is generated. Assuming the pilot makes no correction, the aircraft would yaw to the left. The yaw to the left would increase the lift on the right wing and decrease the lift on the left wing. This would make the aircraft roll to the left, and the rolling moment could not be stopped with roll control. So, if the pilot did not respond to an engine failure in a correct and timely manner, this would happen. The roll would reduce the vertical component of lift and the aircraft would spiral dive. At low altitude, this would be catastrophic. Whenever an engine failure occurs on a multi-engine aircraft, the first thing the pilot must do is stop the yaw with rudder. Asymmetric thrust will be fully covered in later lessons. The second use of the rudder we will look at is takeoff or landing with a crosswind. The landing approach is illustrated with a right crosswind. If you position the aircraft on the extended runway centerline with a right crosswind, the aircraft will drift to the left. What you should do is position the aircraft on the extended runway centerline, but fly it in a direction slightly towards that from which the crosswind is coming, in this case to the right. Please note, you are not using the rudder to do this. You are now tracking the extended runway centerline, but with the aircraft at an angle to the direction of flight. If you were to touch down in this attitude, you would damage the undercarriage. You use the rudder to align the aircraft with its direction of travel. Not too early, or the aircraft will start to drift sideways. Not too late, otherwise you will damage the undercarriage. The third use of the rudder we will look at is something we have already considered: balancing adverse aileron yaw. The fourth use of the rudder we will look at is spin recovery. Full rudder must be applied in the direction opposite to that of the rotation of the aircraft. In this case, rudder to the left. The fifth use of the rudder we will look at is opposing the propeller turning effects. There are 4 propeller turning effects which will be fully explained in a later lesson. We will consider spiral slipstream here. The propeller on the majority of aircraft rotates clockwise when viewed from the rear. Therefore, the prop wash will also rotate clockwise and approach the fin from the left. This generates a left yawing moment. The left yawing moment from the propeller slipstream is balanced by an application of right rudder from the pilot. Consider an aircraft in straight, steady flight. If the rudder is deflected to the left, the camber of the fin is changed and an aerodynamic force, here in blue, will act to the right at the fin centre of pressure. The aircraft will yaw to the left. Ignoring any rolling moment generated by the yaw, the aircraft will continue in the same direction of flight, here shown by the true airspeed vector. The airflow is now approaching from the right, changing the effective angle of attack of the fin, which generates an opposing side force acting to the left, the fin force, here in red. When the fin force equals the rudder force, the aircraft will stop yawing about the normal axis, and a steady side slip angle will exist. The aircraft is not turning, it is side slipping, in this case, to the right. When the rudder is returned to neutral, the rudder force is removed. The fin force will yaw the aircraft to the right, until once again it is in straight, steady flight. You have seen that to hold a constant side slip angle, the rudder must remain displaced from neutral. Therefore, like the elevator, the rudder is a displacement control. As with all aerofoils, the fin has a critical angle of attack, the angle of attack at which it will stall. If the side slip angle is too large, the fin could stall. In this example, we are considering a large crosswind gust. Fin stall must be prevented. The designers can increase the stalling angle of the fin by sweeping the fin backwards, or by decreasing the aspect ratio of the fin by fitting a dorsal fin. The rudder on any aeroplane must be powerful enough for the worst-case event. For the rudder of a large modern jet transport aircraft, the worst-case event is an engine failure at low IAS. At other times, however, that much rudder power would be excessive, so large modern jet transport aircraft are fitted with a rudder ratio changer. The illustration shows a large modern jet transport aircraft at low IAS. Full rudder pedal travel has resulted in maximum rudder displacement from neutral. In this example, we assume the pilot is making a maximum rudder command from the flight deck. You can see that full rudder displacement is available up to about 160 knots indicated airspeed. Above that speed, the rudder ratio changer reduces the maximum available rudder displacement at a rate inversely proportional to IAS to maintain the required rudder authority. To complete this lesson, we will look at the secondary effects of both rolling and yawing. Pitching the aircraft does not give a secondary effect. The secondary effect of roll is yaw. Adverse aileron yaw has already been described, producing a yawing moment opposite to the direction of roll because of the difference in drag from the ailerons on each side. The yaw from the roll is increased by the change in direction of the lift vectors on the downgoing wing and the upgoing wing. Only the downgoing wing is illustrated. You can see that the lift vector acts at 90 degrees to the effective airflow, giving a forward component of lift on the downgoing wing. Thus the yawing moment from the roll is increased. When the aircraft stops rolling, the yawing moment will be absent. We have merely frozen the animation for your further consideration of the vectors and forces. The secondary effect of yaw is roll. In this example, the aircraft is yawed to the left. The right wing is accelerated and the left wing is decelerated. Therefore, the right wing will generate more lift and the left wing will generate less lift. A left yaw will give a roll to the left. A right yaw will give a roll to the right. If the rudder is deflected to the left, an aerodynamic force will be generated to the right, acting through the fin centre of pressure. Because the fin centre of pressure is located above the aircraft CG, a right rolling moment will be generated. Please remember that a moment will not necessarily give movement. You must appreciate that we are only considering the effect of displacing the rudder, not the yaw that would result.